All right, welcome back. Now we're back in module number 2, but now we're into lesson number 3, which is optimizing EIGRP behavior. And in this lesson, we're pretty much going to talk about, it's a really important lesson because it again speaks to essentially what our goals are with respect to designing and implementing a protocol as efficiently as possible. Everything that we're going to see in this particular process is nothing that's going to be required in an EIGRP implementation, but it is certainly something that's going to be necessary for us to be able to make sure that EIGRP is efficient and is operating as as just as efficiently as it possibly can. So we need to talk about the query process, what the effect of the query process will have in our EIGRP topology. We'll talk about how stub routing features work, and what is a stub router. And of course, on the test, you're going to see a stub routing lab. So this is a pretty important concept from that perspective. We're going to talk about the stuck inactive issue. We'll talk about how we do summary routes to reduce the size of a routing table, and also to change the impact of the query process in our topology. And then finally, we'll talk about what are some of the load balancing options that we have with EIGRP, because EIGRP is the only routing protocol that actually has the capability of not only doing equal cost load balancing, but also unequal cost load balancing. All right. So let's start by talking about the query process. We already saw from our previous lesson and our previous discovery lab that EIGRP queries are sent to neighboring routers whenever the router loses its successor route and it doesn't have any feasible successors. The idea here is that we're trying to identify whether or not an alternate path is still a viable path and it wasn't included as part of the original path in the process. And again, this is all based on the fact that we're dealing with a distance vector routing protocol. EIGRP is actually the only routing protocol that even includes the query process as part of the discussion. So queries are sent out whenever a route is lost and there's no feasible successor route. We actually send those queries out to our neighbors. We can see that from router 1's perspective. It lost the 14 subnet. Let's assume that the 14 subnet is just some network behind router 1. It's not directly connected, but we lost the 14 subnet. And so I query router 2 because it's one of my neighbors to say, hey, router 2, do you have a route to the 14 subnet? Obviously, being that router 2 is a stub router, meaning that it only has one way to get to the 14 subnet, it's not going to have a path. But here's the thing. R2 might have to query its neighbors, and R3 and R4 might have to query their neighbors, and so on. So this query propagation process can be quite extensive, and it can take up a lot of resources as they propagate through the network topology. The other problem that we run into is that I can't respond to a query until everybody that I've sent a query to responds to my query. So R2 can't respond to R1 until R3 and R4 respond, and R3 and R4 can't respond until R5, R6, R7, and R8 respond. So that's a bit of a problem, right? It can potentially be a problem because what happens if R5 doesn't respond? It's a domino effect. R5 doesn't respond, but R6, 7, and 8 respond. Well, guess what? R3 can't respond. R4 can respond to R2, but if R3 can't respond to R2, then R2 can't respond to R1. And this is where we get into this whole concept of stuck inactive and what that represents. All right? Now, there isn't really any reason in the case of our topology here that R1 should ever query R2 for any routes that exist beyond R1. Because the only way that R2 gets to those routes is through R1. Does that make sense? So R2 is what we call a stub router. It basically, or a stub, it's attached to a stub network, which basically means that we only have one way in and one way out. So there's really no reason that R1 should ever query R2 for networks that exist, you know, in this enterprise domain behind R1. There's no reason R1 should ever query R2. So what we're going to talk about is what is the process of configuring an EIGRP stub router? How does that help us with this query process? We're going to talk about how it helps with network stability, how it reduces resource utilization, and then how it also simplifies our remote router configurations. And there's several aspects to doing this query configuration that actually kind of solidify this overall process that we're talking about. All right, so let's start by kind of getting into discovery number 4. Let me go ahead and load that up, and then we'll continue on. So we've got the topology loaded. What we're going to be doing in this particular case, EIGRP is essentially already configured on all 3 routers. The HQ router, the BR1A, BR1B, and obviously in this particular case, we're trying to essentially demonstrate how stub routing features work and what the purpose of a stub routing feature is. It's not an overly complex concept. It's actually a relatively simple concept, but it's very demonstrable in that really to understand the effect of using different stub configurations, you really kind of have to see it in action, and that's what this discovery is supposed to do, right? In the case of EIGRP, when we're dealing with the query process, it's really not a very efficient process, and it's almost a necessary evil when it comes to handling how EIGRP and how it handles traffic and whatnot. So queries are something that we actually really just try to avoid as part of our overall design in our topology. Queries get also replied to, and it's just overall, it's just not a very efficient process, especially as the size of the network topology continues to grow. So one of the things that we like to do is we like to go ahead and configure what we call an EIGRP stub configuration. In OSPF, we have a similar concept, although it is actually called a stub concept in OSPF. But in OSPF, the stub features are related directly to area design, not individual router design. So in EIGRP, when we're applying stub configurations, we're applying those stub configurations based on individual routers acting as stubs, as opposed to a group of routers or an area or whatever acting as a stub like we might see in OSPF. So we'll take a look at that as part of this process. So that's essentially what we're going to do in this entire discovery, is just look at all the different stub options that we have. We have 3 routers in this discovery: HQ, BR1A. Let me pull up the slide deck here real quick. BR1A and BR1B. And I just want to point out a couple of things that are already configured in this topology. First of all, BR1A is going to essentially be our stub router. But what's happening behind BR1A is pretty important to understand in order to kind of gauge what's happening in this network altogether. All routers are already configured with the EIGRP in this case. BR1B is announcing a /23 summary into the network, 192.168.16. Let me pull up the actual topology. 192.168.16.0/23, which is actually going to summarize the 16 network and the 17 network. Now, this is all of this stuff that I'm describing right now is being done only because we need to demonstrate a couple of different summary features that exist in EIGRP. This is not how a network typically would be configured, and you certainly wouldn't have all these kind of weird configurations in the topology. So BR1B is announcing a summary route over to HQ to include the 16 and 17 subnets, and then the loopback, the /18, is actually being redistributed into EIGRP. So it's coming into EIGRP as an external EIGRP route. So if I go over to my HQ router, I can see those concepts in the HQ router. Show IP route, EIGRP, and sure enough, I see the /23 coming in as a summary route from BR1A and then subsequently from BR1B. And then I see the .18 subnet coming in as an external route with an administrative distance of 170. So we don't have any stub features configured presently, but we do have a couple of special types of routes that are coming into the topology. That's just part of the pre-configuration. All right, so we're seeing essentially 3 different routes here in EIGRP. The 192.168.0.0 subnet, which is, if you look at the diagram, 192.168.0.0 is the loopback that sits behind here. And then we're seeing the 16.0/23, which is a summary that's being generated by this router here, coming in as a /23, which includes 2 subnets, 16 and 17. And then we're finally seeing the .18 subnet come in as that external route. All right. We're just generating these individual types of routes so that we can identify how each individual stub option works, because there are actually 5 different stub configuration options that you have with EIGRP routers. Let's take a look at BR1A real quick and do a quick show IP route on BR1A. And here we can see that, sure enough, we do have a null 0 route. And I know that null 0 route's being created because there's a summary happening. So actually BR1A is the one that's actually generating the summary route. And we can also see that BR1A sees both, actually it has a static route to 17 and 18. So we're not actually learning about those routes through EIGRP. And then obviously the 00 subnet is directly connected. So that's kind of, we're setting the table to really kind of talk about what it is that we're trying to accomplish here. So let's go ahead and verify our neighbor relationship between HQ. We already know that we're neighbors because we're getting the routes, but I'm going to do a quick show IP EIGRP neighbor, and I'm going to look at the details. And I can see here I'm getting the 3 prefixes from BR1A. I have a neighbor relationship on my Ethernet 1.0 interface, and the neighbor is 172.16.1.2. Simple enough. All right. And we're getting all those routes from BR1A. So we're going to run a debug now, and we are going to essentially just verify that the query process is actually taking place on the HQ router when a route goes down. So on the HQ router, we're going to do a debug, EIGRP packets, and we'll just do the terse output, meaning that we just want to see kind of a summary of each of the EIGRP packets that are coming across. And then I'm going to go into my loopback interface, and I'm going to shut down my loopback interface. Now, just because the loopback interface is directly connected to the HQ router doesn't mean that the HQ router is not going to try and look for an alternate path to that loopback destination. So interface loopback 0, I'll do a shutdown, and I should see, in this case, a query being sent, and then I receive an acknowledgement, and I get the reply back right here, received a reply. We could actually, if we were doing a Wireshark capture, we could actually see that the reply is indicating that that router doesn't have a route. But the point is that I'm seeing the query process take place, sending the query. I receive an acknowledgement that tells me my neighbor received the query. All right, and then I receive a reply, and then I enqueue and send the acknowledgement back to the router, indicating that I've received a reply. All right. So all of that is just part of the process, right? I lost my successor route Technically, I did not have a feasible successor, which means now I have to query my neighbors. All right, so we sent that query over to BR1A. Then the EIGRP uses that query. Obviously, we're trying to identify whether BR1A still knows how to reach that destination and so on. All right. If for some reason HQ loses the path to the 10.1.0.0/16, if I do a quick show IP interface brief on my router here, show IP interface brief, you can see that that loopback was the 10.1.0.1 address, but it's actually the 10.1.0.0/16 network. What's going to happen if my show IP EIGRP topology, I didn't mention this in the last section, but you see the P's here? The P's indicate that the routes are stable, that we've discovered the destinations, we've identified them, and we're not actively looking for a route. But during the process of shutting down the interface, if I was able to actually run the, I don't know, I can give it a shot. See if I can turn off my debugs. No shut. I doubt that I'm going to be able to do it quick enough, but I'll give it a shot. So let me queue up the command, do show IP EIGRP topology. So we have the 10 network back in our topology, 10.1.0.0/16. So let's do a shut. Yeah, see, I can't even do it quick enough. But basically what should happen is during that query process, that route would go active. Unfortunately, our queries don't need to propagate very far. So I'm getting a reply pretty quickly, which means I can't see that active state. But I would technically see, if I'm in a query process, I would see an A next to that entry in the topology database rather than a P, indicating that I'm actively looking for an alternate path to that destination. All right. So what is this stub feature then? I believe based on this topology that you guys agree that there's really no reason to query BR1A for routes that are lost in the HQ cloud, because BR1A goes to the HQ router to get to all those routes. So what we want to do is we want to configure BR1A as a stub router. All right. And that includes any router that I would never want to query. But the stub routing feature has a couple of components to it that are very important to understand. So let's get down to that slide. This is the routing table that we verified, the neighbor relationship. We shut down the interface, did our debug. We were able to see the queries being sent and received. And so now here we are. So I want to configure BR1A as a stub router. The very first thing to understand about configuring stub routing is that any type of router that is configured as a stub basically instructs all of its neighbors that it's a stub router. So there's a little flag. Remember in the EIGRP packet header, there were some flag fields. There was a flag field, and one of those bits in that flag field is called the stub flag, which means that I can identify myself as a stub router to my neighbors. By definition, nobody is allowed to query a stub router. All right? So by just simply making myself a stub, I'm telling all of my neighbors, it's not on a per interface basis. This is done under the EIGRP routing process, so it applies to all of my neighbor relationships. But by setting my router as a stub router, I'm instructing everybody else that I'm neighbors with, don't send me queries. I don't want them. All right? But that's only half of the stub configuration. What you're seeing on the slide here is a representation of all of the different options that I can include in the stub feature. So if I come into BR1A and I set BR1A as a stub, HQ will never query BR1A, and BR1B will never query BR1A if it loses routes. all right? But we're also going to restrict what BR1A advertises back to its neighbors. That's the second part of a stub configuration. What does BR1A advertise back to its neighbors as part of this stub configuration process? And that's what these 5 options represent. If I say EIGRP stub connected, then the stub router is going to only advertise connected routes that are part of the EIGRP process. If I say EIGRP stub summary, then the router is going to only advertise summary routes that are part of the EIGRP process. If I say EIGRP stub static, then I'm going to only advertise static routes that are redistributed into EIGRP. If I do EIGRP stub redistribute, then I'm going to only advertise redistributed routes in EIGRP, which could include static, but it could also include OSPF, connected, any type of route that's redistributed into EIGRP. If I say stub receive only, then I'm only going to, I'm only going to accept routes. I'm not going to send any routes to my neighbors. So you might look at this and say, well, that doesn't really have anything to do with the query process. And it's true. Filtering what routes I send to my neighbors as a stub router really doesn't have any effect on the query process, but it allows us to add another level of efficiency in EIGRP to reduce the amount of bandwidth that's being utilized over a link and just to reduce the amount of work that routers have to do to converge. And that's really what this feature is all about. It's about that process. All right?
So just real quick, for me, I had to step away for just a second. So just so I understand, the BR1B loses a route or path. It's not, you're configuring BR1A as a stub so that it doesn't receive any queries because it can't help BR1B essentially, right?
Right.
Okay.
Sorry, go ahead, continue.
No, go ahead.
Yeah, if BR1B loses its a loopback. So to answer your question, yes. So if BR1A is configured as a stub router, then BR1B would never query BR1A for any routes that it might lose, right? So we've got loopbacks there, but there might be networks behind BR1B. And again, BR1B as a stub is connected to a stub network from the perspective of BR1A, and then BR1A is connected to a stub network as from its perspective to HQ. So there's any networks that I lose behind BR1B, there's no reason why BR1B would then query BR1A for those networks because there's no way to get to those networks other than through whatever BR1B is connected to. So,
right, so if HQ had a connection to BR1B, then you wouldn't want anybody to be a stub at that point, right?
Okay, let's walk through that scenario. So let's say HQ had a connection to BR1B. Would I want to configure BR1A as a stub? And the answer is no, you're correct, because HQ would want to be able to either choose this path or choose a path if I have a link between here. And in that case, it's not a stub router. However, it is still possible that you might want to do that because you still don't want the HQ router querying BR1B and BR1A for networks behind HQ that might go down. So remember, the only time a query process takes place is if you don't have a feasible successor. So you have to analyze the topology and say, okay, for all these routes behind BR1B and BR1A, does HQ have a feasible successor for those paths? If HQ does have a feasible successor for those paths, then yeah, you would configure BR1B and BR1A as a stub because HQ wouldn't have to query them anyway for networks they might lose, networks that might go down behind these routers. Does that make sense? So let's say I have a link. I'll draw it in here just temporarily. So I have a link here, and so now HQ can reach these loopbacks through two different paths. if this happens to be the primary path, but this secondary path meets the feasibility condition, then I can still configure these guys as stubs because a query process wouldn't take place anyway in the failover process. And I would still want to eliminate HQ from sending queries to BR1B and BR1A for networks that are behind HQ. You know, maybe I've got my corporate enterprise back here and there's thousands of networks. I don't want HQ sending out queries to BR1B and BR1A every time some network behind HQ goes down. So the answer to that particular question is, well, it's kind of twofold, right? Yes and no. It just depends on your understanding of the design elements and making sure that the design is done correctly. Did that make sense, that explanation? Yeah. Okay. All right. But obviously in this case, because these are both stubs, we're gonna go ahead and configure BR1A as a stub router, and it's gonna notify BR1B and it's gonna notify HQ through that stub area flag, through the stub flag in the EIGRP packet header. Hey, I'm a stub. Don't query me anymore. Okay. So let's take a look at. So as far as the actual stub process goes, for the purposes of configuring a router so that it does not respond to query or doesn't get queried, that's a very simple process. You're basically just going to configure the router as a stub, any kind of stub. Could be connected, could be summary, could be whatever you want. But the bottom line then is that that router is not going to be queried. Okay. But there's a secondary process to this, and that's what people get lost with the EIGRP stub configuration, is they forget that it also affects what the stub router sends back to its neighbors. Not just that I'm not going to query the stub, but what does the stub router send back to its neighbors? So let's go ahead and we're going to configure kind of each one of those. Notice here, this is a test question, so that's important. The default is connected in summary. So if I don't specify a specific stub option, then the default is going to be connected in summary. So let's go ahead and configure BR1A as a stub and see what happens. All right, we're going to see that the adjacency is going to change a little bit. We're going to have to do basically a soft reset on our adjacency because we're actually changing the components of the actual hello packets. So we go config T. Now let me do a show IP protocols real quick. Make sure I know what process ID, what AS we're using, AS1. So config T, router, EIGRP1, EIGRP stub. All right, that's pretty much it. Just EIGRP stub. We see the adjacencies go down and the adjacencies come back up. And now HQ, both HQ and BR1B are getting hello packets from BR1A, but inside that hello packet, we're getting that stub flag. That stub flag is set so that it tells those routers, hey, don't query me, right? So let's do a end here. We'll go to our HQ router and turn off our debugs. Let me show debug. I don't know if I'm running any debugs. No, I'm not running any debugs. Okay. And let's take a look at the neighbor. Show IP EIGRP neighbor. Now, if I just did a show IP EIGRP neighbors, I wouldn't necessarily see any reference to stub. I don't really identify that router as a stub, but if I add the detail option, I can see that I'm suppressing queries for that particular neighbor, and the stub is only advertising connected and summary routes back to me. All right. Now, if I do a show IP route EIGRP, I would expect, remember we had 3 different routes. We had the loopback that was connected to BR1A. We had the summary route that was generated by BR1A, and then we had the redistributed static routes coming in as DEX. I should not see those static routes anymore because I'm suppressing redistributed routes in the advertisements back to the HQ because of my stub configuration. And sure enough, that's what we see. We only see the 192.168.0.0 route, and we only see the 192.168.16.0/23 route. If I go back to BR1A, I'm not suppressing any routes coming in to BR1A, because remember, the stub feature does not suppress what BR1A is receiving. It just tells everybody, don't query me. So I'm still getting the 10 network. Oops, I got to turn that puppy back on. Hold on one second. Interface loopback 0, no shut. All right. All right, so I'm still getting the loopback route from HQ. I'm still getting the, I'm still generating the summary route. Remember, we talked about this, guys. You see a null zero route, you know that that's the source of the summary, because you'll never see it. Well, you could do static null zero routes if you want to do black hole routes and stuff like that for security reasons. But I know because this is a D route, EIGRP, and it's null zero, that I'm the one generating the summary in this case. And I see my two static routes that go over to BR1B. All right. But now the routing table in BR1A didn't change because it's a stub router, but the routing table in HQ changed. We saw that already. We didn't see the redistributed routes. If I do a show IP EIGRP topology, I can see the summary is here, and I can also see the 18 route, and I can see the 17 route, which are being sent into EIGRP as a redistributed route, coming in as through a redistribute static command. Remember, my stub configuration. My stub configuration is just EIGRP stub, which means connected in summary. All right. So now let's just do stub connected. Config T. Get back to the window. Config T. Router EIGRP1, EIGRP stub connected. By the way, on the exam, you have to remove the old EIGRP stub command and then put in the new one, just FYI, for that lab on the test, because it doesn't let you overwrite it. Also, one of the tasks in that particular lab is you have to configure a summary on the middle router, and the lab is buggy, it's broken. So if you try to do the best possible summary, which you're trained to do by including only the networks that the router knows, the summary doesn't work. Use a /16. You just summarize to the major classful boundary. It takes the command, but then it doesn't work. That's some of the problems with some of these questions on the test, is they don't work the way they're supposed to. Anyway, so we did a EIGRP stub connected. Of course, now if I go back to the HQ router and I do a show IP route EIGRP, then all I see is the 00 and the 16. Now, how come I'm seeing the 00 and the 16? If I do a show IP EIGRP neighbor detail, I can see that I'm getting the suppression, and I'm also only getting connected routes. Well, if I go to BR1A and I do a show IP EIGRP topology, I can see that the 16 network is connected. It's in the topology database, which means it must be part of EIGRP, and the 00 network is also connected to loopback 0. So basically, we're just seeing the two physical networks that are connected, the loopback and the 16. This one's not included because it's a connected route on HQ. Connected does not mean any connected route. Connected means the connected routes that are running EIGRP. So if I had another loopback on BR1A that wasn't part of the EIGRP process, it would not be advertised over to HQ as part of the process. So that's why we're seeing those two routes in the HQ router. All right, let me kind of scroll through here, all the little steps that we did. There's our stub connected. There's our show IP EIGRP neighbor detail, show IP route. All right, and then so the next thing they want us to do is set it up as receive only, which is, by the way it's going to be set up on the exam, receive only, and they're going to ask you why isn't this router receiving routes. So EIGRP stub receive only. All right. Neighbor relationship changes again. If I go back to my HQ router, I do a show IP route EIGRP, I'm not going to have any routes because everything is being suppressed. You might say, well, why would I ever want to do that? Well, maybe on my HQ router, maybe there's about 1,000 routes behind BR1A, but they're all contiguous. So maybe on my HQ router, I decide that I'm just going to go ahead and just put a static route for all those routes. And you say, well, then why wouldn't I just do that both directions? Well, maybe there's 1 million routes behind HQ and I don't want to do that and they're not contiguous. So I want HQ to still be able to advertise its routes to BR1A, but I don't necessarily need BR1A to advertise its routes to HQ. Very specific scenario, but I honestly I haven't run into an actual implementation out in the real world that included that, but nonetheless it's a scenario that could exist. All right. So now we've got this guy configured as receive only. If I do a show IP EIGRP neighbor detail, I can see that no routes are being advertised, receive only, pairing advertising, no routes, and I'm suppressing queries going to that neighbor. I would see the same thing on BR1B, by the way. And we already looked at the routing table on HQ to indicate that the routes are gone. All right. Still, BR1A is going to have all of its routes. Do show IP route EIGRP. So I can still I still see the route from HQ, the 10100 route from HQ, so that's not a problem. All right.
Can you go back to that HQ router real quick? I know this seems like it should be a simple thing to understand, but I'm having a...
Sure. What's the question?
Yeah. So you made the A router receive only, and so it doesn't advertise any routes to HQ.
Correct.
HQ knows that it's in receive only based on header information, right? I guess.
It's in the packet header. Yeah, the EIGRP packet header has a couple of flags that indicate that it's a stub router and what kind of stub router it is.
Right. So the suppressing queries line there at the end, was that also there when the A router was doing summary and connected?
Yes, it was, because regardless of whatever you're sending back, in every case, a stub router never gets queried, period. So it could be any stub configuration, and you're going to suppress queries to that router because it's a stub. What doesn't matter if it's stub connected, stub
so that allows so connected and summary still allows HQ to send traffic to A without having to query it, essentially.
Well, yes. So if we go back to the list here, all right, and now that we've kind of gone through the config, if I go back to the list of all the options, all right, these are the 5 options that I have, technically 6 if I just do stub, that I have when it comes to managing what gets sent from router BR1A to HQ. Understand that in every single one of these scenarios, queries get suppressed. That is a common function of the stub process. No matter what, queries get suppressed. Okay. But the secondary piece to this is, what is the stub router going to then send back to its neighbors? Connected, summary, static, redistribute, receive only, or connected and summary. And you can actually combine any one of these. You could say EIGRP stub static summary, or EIGRP stub redistribute summary, or whatever. So you can do kind of multiple combinations if you want. All right. What you're suppressing is what BR1A is now advertising back to the non-stub routers. Does that make sense? We're suppressing what BR1A is going to advertise to its peers based on the stub configuration. Now, I understand the logic in the question, because I get this all the time with this particular example. To me, to you, that's probably saying, well, wait a minute. What if HQ wants to get to those networks and BR1A is not advertising them? Well, then you're going to have to configure an alternate method for HQ to get to those networks. It's usually going to be a static route. All right, so it has to be a specific design scenario that's going to decide how you handle that piece of it. As to what method you choose. But you're right. If I do receive only on BR1A, BR1A is not going to advertise any routes to BR1B, and it's not going to advertise any routes to HQ. There's still going to be neighbors, which means HQ can still send all of its routes to BR1A. But in order for HQ to reach any of these networks behind BR1A, there has to be another routing method that's chosen to do that. Does that make sense?
Right. And it does, yeah. And explain to me again real quick the query process. So the query only happens if a route is lost, or does it happen in other situations as well?
There's a couple of different scenarios where queries happen, but ultimately a query occurs when I lose my primary route, my successor route, and I don't have a feasible successor. Okay? And in the case of...
How resource intensive is that really?
How resource intensive is a query?
Yeah, I mean, you're saying, I don't want to send that traffic over there because it's useless traffic. That router isn't going to get me to the network that I dropped anyways, so why have that traffic go over there? But why all the concern about it, I guess?
It's not so much that the query packet itself is resource intensive. It's the way that queries propagate through the network that makes them very inefficient, right? So
that's right, because you were talking about the chain effect.
There's a chain effect,
one
right?
Doesn't respond to the other, then
in this particular topology, you're not really gaining anything by suppressing queries because there's just not enough routers to make a difference. But if you have hundreds of routers, or if you have a highly redundant and dense network topology, absolutely you can run into a situation where queries can overwhelm the network. And then we're going to also talk about in the next section here stuck inactive, and how stuck inactive conditions can affect adjacencies and neighbor relationships. So I have to be honest. I have designed a bunch of networks. I've implemented tens of thousands of networks probably over the years, and I have never configured stub routers in an EIGRP domain. Now, granted, I haven't worked on networks that had 10,000 routers, or that's a little bit ridiculous, but 100 routers or even 200 routers. I've only worked on networks that maybe at most had 30 or 40 routers, but I tend to use summaries a lot more than I do the stub routing feature, just because either I know that there's feasible successors in my paths and I'm not even going to see the query process, or I'm just not really concerned about it. Okay? So in this particular case, I would say that using a stub routing feature is probably not something that you would normally design into your enterprise, but you do need to be aware of what it does and what the potential is for that feature in case you do run into a scenario where that might be useful. Does that make sense? All right.
And so the query is message to a broadcast to all routers in the routing domain. Hey, who has information about this route? Right? That's somewhere.
Yes, that's absolutely correct. Absolutely correct. All right. So the process, I mean, for the testing purposes, obviously for exam purposes, your primary goal here is to obviously understand the process. But, you know, again, this is just something that that you're not normally going to include in as a standard design element in EIGRP. But let's talk about what potentially could occur in a situation where I have kind of a robust network and these queries start going out and propagating through the network. All right. The first thing that we run into is a situation called stuck inactive. We know that EIGRP uses reliable multicast packets to search for an alternate route through the query process. But during that process, EIGRP cannot make a decision until it receives a reply for every single query that it generates in the network. All right, that means we're in an active process, and we're now trying to find an alternate path, and I'm querying all of my neighbors to be able to try and identify that alternate path. But let's say I query 10 different neighbors, I need to get a reply from all 10 of those neighbors before I decide on what I'm going to do. Does that make sense? So once a router goes active and it starts incrementing or sequencing these queries, it can only come out of that active state and go back into a passive state when it receives a reply for all of the queries that it generates. All right? If that doesn't happen within 3 minutes, I go into something called a stuck inactive state. You can modify that timer, but the default timer is 3 minutes. Here's the worst part about that. By the way, that's called an active timer, incidentally, but it's not really that important. Active timer meaning that I'm in an active mode trying to find a route, and I'm querying my neighbors to try and figure out what the heck's going on. All right, so I'm actively searching for an alternate path. If I go stuck inactive, I essentially delete or remove the neighbor relationship that I'm waiting for query replies from. So let's say, for example, in this topology, R1 loses the 14 subnet, so it queries R2. Excellent. R2 then queries R3 and R4. Excellent. The gray lines have not happened, by the way. In fact, this gray line shouldn't even be there. The one between R2 and R3 shouldn't be there, and the one between R2 and R1 shouldn't be there, because the reply never came back from R5. So R5 doesn't reply to the active query, which means R3 can't respond to R2. Now the problem is somewhere between R5 and R3. But if R2, and this isn't the way it works now, but this is the way it used to work. If R2 doesn't receive a reply from R3 within a 3-minute window, it deletes the neighbor relationship with R3. Even though R3 didn't have anything to do with the issue of the traffic not coming from R5 to R3. You can see where that could be definitely a big problem, right? What would cause a reply to get lost? It could be congestion on the link. Maybe R5 is too busy to respond or whatever. Again, we're talking about a very specific scenario where that would have to happen, but nonetheless, it is a scenario. So EIGRP has been redesigned to handle this so that we don't end up deleting that neighbor relationship between R2 and R1 because R3 couldn't respond. All right, there's a secondary query called a stuck in active query. It's a secondary query that gets sent out at half the time of whatever the stuck in active timer is. So if the stuck in active timer is 3 minutes, a stuck in active query gets sent out in 1.5 minutes. All right. So let's take a look. So let's say we'll go through the same scenario here. R1 loses the 14 subnet. It sends a query to R2. The timer starts. R2 sends a query to R3. The timer starts. R3 doesn't respond. Within 1.5 minutes, R2 is going to send a second query called the stuck in active query over to R3. And then subsequently, R1 is going to eventually do the same thing to R2, because R1 says, well, you haven't responded in 1.5 minutes, R2. But because R2 responds to the stuck in active query with a stuck in active reply, R1 says, oh, okay, well, it must not be you then. Something else must be happening that's preventing you from responding to my query process. If R2 sends a stuck in active query and it doesn't get a response from R3 within a specific amount of time with a stuck in active reply, then R2 proactively deletes the relationship with R3, and then R2 can now respond to R1's query. Does that make sense? So it's a way of isolating where the actual failure event occurs. But you have to understand that in this process, if I had a backup route, I wouldn't be using it during this process, because I have to wait for all the queries to come back before I can decide that that backup route is even a viable path, if I did have a backup path. If I don't have a backup path, none of it really matters, because I'm not going to be able to route to it anyway. So the timers don't matter. Whether or not a router replies or not doesn't matter. Obviously, the fact that I can't get a query reply back from R3 indicates there's probably some other problems going on there. So I'll probably have to investigate that and make sure I understand what's going on there. All right. You're really quiet. Can you turn up your mic a little bit?
Oh, sorry.
Or just talk a little bit louder. What was the question again?
Can you go back to the previous diagram?
Yeah, sure. Yeah, go ahead.
So R3 is still receiving routes from R6. Why would he break his neighbor relationship with R2?
Well, that's a great question. Yeah, I mean, that's a great question. I mean, it doesn't seem very, doesn't seem very polite, obviously. Or what the question was, look, R3 is getting responses from R6, and R3 is still sending routes to R2. So why would R2 decide to delete the relationship with R3? Well, that was a design flaw in the protocol. Basically when Cisco developed EIGRP to start with, they said, look, if I'm not getting responses to queries, then there's something wrong with that neighbor relationship. And there's something bad happening in that scenario. So instead of just letting the network hang and not do anything, I reset that neighbor relationship. Now, it's not that the neighbor relationship can't come back. It's not that I'm deleting the neighbor and I'm disallowing that neighbor to ever establish an adjacency with me again. I'm just going to kickstart the neighbor relationship over again. And hopefully in that process, I'm isolating the problem in the network, because I'll reform my adjacency with R3. R3 is going to kickstart its relationships with R5 and R6. And most likely R5 is not going to be able to establish an adjacency with R3, because if it can't send query replies, then it's probably got some other stuff going on. Does that make sense? So it's kind of like killing a fly with a sledgehammer, but the idea is that we're trying to recover from something bad that's happening in the enterprise, whatever that might be. All right. So it's just going to require some additional reconvergence and relearning of everything. But in the end, we hope that that kind of isolates the problem and fixes the problem. Now, there's really no reason that R2 should ever delete its relationship with R3 because there's no problem between R2 and R3. And that's why when they redesigned the protocol, or enhanced the protocol, if you will, they added this stuck in active query and stuck in active reply process to further isolate the issues and figure out where those issues reside. Does that make sense? So now only the relationship between R2 and R3 are going to be affected and not the relationship between R1 and R2. All right? All right. Now, there's another way that we can kind of help with kind of reducing the load on the network, and that is to simply configure summaries. If I create a summary route that includes these networks behind, well, this is a supernet, huge summary, 192.168.0.0/16, which clearly would include those two networks, but it would include a whole bunch more. If I send in a summary, even if this 12 network goes away, the summary doesn't change because the summary route is still valid. It still includes the 18 subnet, maybe any other subnet that might be included in that summary. So if I have a summary coming in from HQ to the gateway, there's no need to send in a query and a reply. At least from the gateway perspective to the HQ perspective. Now, I still have to send a query out. So if the 12 subnet, for example, goes away, I'm still going to send a query to the gateway router, and the gateway router is going to respond that it doesn't have an alternate path to the 12 subnet, but the gateway router is never going to query HQ for a bunch of 192.168 networks that might go away. All right. So this is really kind of the better, to me, it's really the better way of handling the process of managing the scalability of EIGRP is to make sure that you're putting in appropriate summaries into your topology so that you're reducing the size of your topology database. So let's go ahead and go into the next discovery, which is discovery number 5. How do we set up EIGRP summary routes? So we've got our topology configured here, EIGRP summarization. Clearly we can see on BR1 and BR2, we've got a bunch of routes that we're going to go ahead and summarize. Let me pull up the diagram here. So our goal in this particular demonstration or this discovery is to announce a default route from HQ into EIGRP so that BR1 and BR2 will get a default route. And then also to summarize the 10, 11, 12, and 13 subnets behind BR1 and to summarize 64, 65, and 66 behind BR2. And that's what our goal is here. Okay, so let's take a look at, obviously we can understand the need to do this summarization and why that's important. If I go into my HQ router right now, I will see a whole bunch of routes. Show IP route, EIGRP, and so I can see 1, 2, 3, 4, 5, 6, 7 different routes. Doesn't seem like a lot, but if you can extrapolate this to a real enterprise type of environment where you have potentially hundreds of routers or maybe even thousands of routers, you could have 10,000 routes, and summarization can obviously have a huge impact on that number of routes in your topology if you need to reduce the amount of routes in that particular case. So we're looking at this on kind of a smaller scale, but nonetheless the concept is still the same. Now we already talked about the concept of auto summary. Auto summary means I'm going to summarize to a classful boundary. So let me do a quick show IP protocols and make sure I know what my autonomous system number is, AS1. Config T. router EIGRP1 auto-summary. All right. Now there's a specific problem with this, as you can probably imagine, because if I go back to HQ and I do my show IP route EIGRP, I still see the individual routes that are coming from the other router, and now every other one of those routes has been summarized to a major classful boundary coming from router BR1. This would actually technically still work, but it's again not very plausible, especially if you happen to do auto summary on both routers. All right, and that's where we really run into an issue, is where we do auto summary on both routers. Then I might decide that I'm going to load balance. In fact, let's just go do it and see what happens here. So I'll come into config T, router EIGRP1 auto-summary. So now if I go over to HQ, I actually look like I can load balance to those 10 networks. Now if I do a ping, let me grab one of those networks here, show IP interface brief, 10.10.01, it might actually work. All right, and if I ping 10.11.01, it fails. Actually, there's a reason why it worked, and one worked and one failed, because we have this little thing running called Ceph, and Ceph caches routes and whatnot. So if I actually turn off Ceph, which hinders load balancing and all kinds of other stuff. If I do a ping to 10.10.01 now, one packet gets there, one packet doesn't, one packet gets there, one packet doesn't. And if I ping 10.11.01, one packet gets there, one packet doesn't. So what's basically happening is the router is load balancing. It's sending one packet one interface, it's sending the other packet the other interface. It's just not good, right? Because we've got the router confused. It thinks that it can get to all those networks through two different paths. So let me go ahead and turn on IPsec again. And let's go ahead and get rid of the auto summary option. Oh, by the way, show IP route here, you're going to see that null zero route as well, because you're actually creating that summary. And whenever I generate a summary, I always put in a null zero route, which also is bad in what sense? Now I can't get to the other 10 networks. If I ping from BR1 or BR2, excuse me, again, do show IP route. Let's just include 10. You can see that I've got null zero route and I've got the local routes, but if I try to ping, well, we know it's not going to work. 10.10.01, it's going to fail because I'm not seeing the 10.10 route because it's being summarized. So anyway, auto summary, bad situation. You don't want to run it. So let's do no auto summary and get rid of that. And we'll do the same thing here. No auto summary here as well. All right. All right. So what's the other solution then? The other solution then is to go ahead and do manual summarization, where I want to actually summarize the route based on what's actually included, not just some sledgehammer approach to doing a route summary. Incidentally, we've already gone through several of these slides here. Let me just kind of scroll down. We did the show IP route. We saw 7 routes. We did auto summary on router 1. We saw that auto summary route. And we saw the null zero route on router 1. And which also, we can still see the 64, 65, and 66. So far, this is not a bad deal. But it ultimately ends up leading to a bad deal when we add the auto summary feature on to the second router. And we now can see that the router thinks it can load balance. HQ thinks it can load balance. And we had to disable Ceph for this to happen, but we get a timeout. Actually, in this case, Ceph is not disabled. We just happened to pick, when we pinged 10.10.01, Ceph had already decided that it was supposed to go over a different link. So we take out that no auto summary. All of our routes show up again. There's all 7 of our EIGRP routes. 1, 2, 3, 4, 5, 6, 7. So now we need to go ahead and calculate our summaries. We actually did this exercise in one of our previous lessons. I think you guys remember when we did that. I showed you that essentially to do summaries, you just want to basically find all of the common bits. And in this particular case, for 10.10, 10.11, 10.12, and 10.13, the first 8 bits are common to every one, which is the 10. And then 9, 10, 11, 12, and 13 are common. So the value of this octet is 10, which is how we get the 10. The value of the bold bits here is 8, because this 8-bit is on. We use our powers of 2 radix scale to identify the decimal weight of each place in a binary string. And that's how we got this summary. 10.8.0.0/13 allows us to summarize network 10, 11, 12, and 13. There's actually another way to look at this. We know it's 4 routes that need to be summarized. It's 10, 11, 12, and 13 that need to be summarized. But you can only summarize in blocks. All right? I can create a summary of 2, 4, 8, 16, 32, 64, 128. I don't have any other choice. That's all I can summarize to is blocks of addresses. 1, 2, 4, 8, 16, 32, 64. So you might say, okay, well, great. I'll just summarize this as a block of 4. But here's the golden rule. You cannot, the block size of summary addresses that you're creating needs to be evenly divisible into the address that you're starting the block with. So the biggest block of summary addresses that I can create starting at 10 is 2, because 10 divided by 4 is not an even number. So now I go down to my next boundary, which is 8, 10.8. I can do a summary range of 2, I can do a summary range of 4, and I can do a summary range of 8 if I start at 8, because 2, 4, and 8 are evenly divisible into 8. Does that make sense? It's kind of a little trick to identify what summary blocks you're allowed to create. So there's no way to actually summarize these 4 networks in one nice, concise block. I actually have to start at 10.8, and I have to do a block of 8. All right? Which is going to include 10.8, 10.9, 10.10, 10.11, 10.12, 10.13, 10.14, and 10.15. Okay? Again, if you want to just do it the mathematical way, you just write all the addresses out in binary. You find out which column, what the last column is, where all the bits match, and then that becomes your summarization boundary. And then you go from there. All right? You create your subnet mask, you create your starting address, and that becomes your summary. All right? And we'll do the same thing with the other side as well. So let's go ahead and configure our summary. This is what it's going to look like. Whenever you're doing summaries in EIGRP, you summarize on the interface that you want to advertise the summary out of. Okay? That wasn't a very grammatically correct sentence, but we place the summary on the interface that's going to essentially end up advertising the summary. All right? And we use the IP summary address command to do that. So let's go into BR1. And in our case, I don't know if it's Ethernet. Let's do a show IP interface brief real quick. Yep, it looks like it's Ethernet 1.0. Interface Ethernet 1.0. Oh, geez. IP summary address EIGRP 1, 10.8, .0.0. Now on the test, in the real world, you can do a prefix notation, but I'm not sure that that works on the test. So you can actually do either prefix notation or dotted decimal notation. A /13 is equivalent to, what is it, 5 more bits in the second octet, right? So that's going to be a 248. Yes, 248. 255.248.0.0, because a 252 would be 6 bits, a 254 would be 7 bits, and a 255 would be 8 bits. So you can do it in either format, all right? Either one is equally useful. Give me 1 second. My batteries are about to die on my microphone. Hold on. All right, we've created our summary. Let's go check and see what's happening. Now, first thing we know that's going to happen is we're going to see a null zero route being created on this router, right? And sure enough, there's our null zero route, 10.8.0.0/13, and that's a summary route. I want you to notice something as well here. Do show IP route 10.8.0.0. Notice that it has an administrative distance of 5. By default in EIGRP summary routes have a local administrative distance of 5. So they're actually trusted more than really any other type of route, with the exception of a connected route and a static route. So that's kind of important to note. But if I go to my HQ router, it doesn't stay as, it's still advertised as a normal EIGRP route. So if I do a show IP route EIGRP, I can see the summary here, and it comes in as a D route, which is a 90 administrative distance of 90. So there's a couple reasons why we wanted to make sure that that null zero route gets inserted into the local routing table, because of the importance. For example, let me go ahead and do a quick debug. So I'll do a debug IP packet. Actually, let me just do a debug IP ICMP. I don't want to kill my router. And I'm going to go ahead and ping 10. Well, we know that 15 was not included. Yeah, come on. Ping 10.15.1.1. So HQ, of course, is going to think that it can get to 10.15 because it's part of that summary. And we can even see, I closed it. Dang it. Did I do the, yeah, I did it on BR1. Let me console back into BR1. All right. So I can actually see that the pings are getting to BR1. So I know that the route is working, and we can also, there's some other debugs we can see to indicate that the route is dropping into the null zero bit bucket, essentially. We can do some other debugs and kind of identify that. But so the null zero route's doing exactly what it's supposed to do, which is to make sure that we're not creating a routing loop in our network by sending those routes somewhere else. All right. So we'll turn off that debug. Now, what if we were going to do a summary on the other router? Well, it'd be the same process, right? In this particular case, in the topology here, we're trying to summarize these 64, 65, and 66. So now let me ask you guys a question. 64 is evenly divisible by 2. So I could create a summary that includes 64 and 65, but 64 is also evenly divisible by 4, which means I can create a summary that includes 64, 65, 66, and 67. So let me go into BR2. Show IP interface brief. And we're going to go on Ethernet 1.2, config T, interface Ethernet 1/2, IP summary address. EIGRP1 10.64.0.0. Now check this out. We know that we want to do a block of 4, right? I already know that I can do a block of 4 starting at 64 because it's evenly divisible. So what value of a subnet mask gives me a block of 4? Do you know the way that you calculate that? 256 minus 4, which is 252. So I would put in 255, 252.0.0, and that becomes my summary, which incidentally is a /14. All right. I have a YouTube channel. I'll put it in the chat window here, where I've recorded, I don't know, I've got probably over 150 videos out there. But one of them is a concept of summarization, subnetting. I mean, there's all kinds of great videos out there. Don't forget to like and subscribe, by the way. I got to say that. But we don't monetize our channel anyway, so it doesn't really matter. But if you really want to see all the good stuff that goes out there, my entire CCNA course is out there. I just put the SISAS course out there, which is the Cisco ICE course for CCNP security. I've done my CISSP course I've put out there. I'm going to actually put these videos out there as well. So yeah, all kinds of stuff goes out there, and just spread the word. We love to share information and knowledge. So we got our summary done. As expected, we should see a null zero route. Do show IP route, include null, and sure enough, there's our null zero route. And we went from 7 EIGRP routes down to 2. All right, so it's not a huge savings, but it is definitely valuable. All right, so 209.165.202.129. That's going to be our internet route. So this will be the last thing that we talk about. Let's just go ahead and flip through the slides real quick. Make sure you guys feel that we covered everything. There's our null zero route. We went ahead and did our summary on BR2, and we get our 2 routes coming into our 2 summary routes coming into our HQ router. The next thing is we've got this default route 209.165.200.226. I could configure static default routes on my other 2 routers to simply just route to HQ for the internet, but I can also essentially have the HQ router advertise a default route into the EIGRP process as part of the EIGRP process. There's a couple of ways of doing that. Your best bet with EIGRP is just to simply redistribute the static route, the static default route. You might have to use a route filter, a route map and such to filter out what routes get redistributed. But there is a default network command. We'll talk about that as well. So right now we can look on BR1 and BR2, and we can see that both BR1 and BR2 don't actually have a default route. Do show IP route. Pipe include 0.0. Well, that's not going to work. 0.0. And we don't have any default route. And the same thing would be for BR1. So obviously, in order for BR1 and BR2 to get to the internet, they're going to have some sort of default route. HQ can get to the internet no problem because it has a static default route. That was already previously configured. And that was done with using this static route. IP route 0.0.0.0, 0.0.0.0, 209.165.200.226. So there's 2 ways, like I said, that you can announce a default route into the EIGRP process. One is to basically redistribute a static default route, and the other is to use the IP default network command. I do not like the IP default network command. I think it's extremely confusing. The way that it has to be implemented is very, very specific in the process that you have to implement. You have to use to implement the default route. But we'll talk about both options here. All right. Now, before a router can actually advertise a default route itself, it needs to examine what the default route candidates are. In this particular case, our default route candidate is being introduced into the routing process by using the static IP route command, and the interface that we specified, or in this particular case, the next hop address, is where the default traffic is going to be sent to. We can choose to redistribute that static route into EIGRP, or like I said, we can use something called the IP default-network command. In OSPF, we have something called default information originate. In in RIP, we had something called default information originate. Unfortunately, we don't have that option in EIGRP. All right? So based on the configuration, the router can examine all of the default candidates, and then it's going to select the best candidate based on administrative distance, and then if there's a couple of default routes that are common to an individual routing process, then we look at something like a metric. All right? So we're going to do it in a way that we're actually just going to simply redistribute the static routes, which I think is really the easiest way. You have to be careful with this method, but it is the easiest way to get a default route into EIGRP. First thing I want to do is I'm going to do a show IP route static and just make sure that I only have one static route. If you have more than one static route, you definitely need to make sure that you have some sort of filtering process applied to redistribution, so that you only redistributing the default route. We're going to talk about how to do that in another module a little bit later on. That's actually what we're going to talk about right after our OSPF section that we're going to cover tomorrow. Okay? We're obviously not going to finish EIGRP today, but the last few chapters are pretty quick, and then we'll get into OSPF for the rest of the day tomorrow. So it's really simple. Config T, router EIGRP1, redistribute static. That's it. And if I do a show IP EIGRP topology, I will now see that 000 route is right here, right? The 000 route is now part of the EIGRP process. It's being sent into EIGRP as a redistributed route. And then if I do a show IP route here, I can now see that route's coming in as a DEX route. The asterisk in the route just simply indicates that it's a default candidate, that it's a default route. So that's pretty simple. Like I said, though, you definitely need to be aware of how that process could include other static routes that you may not want to redistribute. So just something to keep in mind. All right?
Hey, that EX is external, right?
EX stands for external. That's correct. EX stands for external.
Right, so why so these are in different routing domains, or why is it that static route?
Well, a static route is not part of EIGRP by default. It's a static route. It's just another routing method. So it becomes an external route because we redistribute it into EIGRP. That makes sense?
Yep.
All right. So I know it's 3:15. So we have another discovery, but let me pause and see where we're at. So we're going to wrap up this lesson by talking about how EIGRP handles load balancing. Load balancing is not a unique feature to routing protocols. Just about every routing protocol, with the exception of BGP, does automatic load balancing, where it can take paths that have the same metric and utilize those paths at the same time. But EIGRP is kind of unique in a sense that not only does it do equal cost load balancing or equal metric load balancing, it has the capability of doing unequal metric load balancing, which is disabled by default. And we can manipulate how this happens and how this works by a couple of different ways. Number one, we can change something called the maximum paths command. So if I come into my HQ router, for example, and I do a show IP protocols, I can see that in this particular case, I have a maximum path count of 4, which means that I will load balance over 4 paths by default as long as they have the same metric. In fact, if I do a show IP route, I can already tell that I'm actually load balancing to the 192.168.0.0 subnet because I see 2 individual entries for a single route and they have the same metric, which indicates that these are 2 successors, and so I'm doing equal cost load balancing. If I do a show IP route 192.168.0.0, I can actually see that the traffic share count is equal. Traffic share count here, traffic share count here. So I'm actually sending, it doesn't quite work out to be a per packet type deal, but I'm actually sending essentially the same amount of traffic over each link consecutively. Now, the problem with load balancing over equal cost paths is that we use typically a fast switching technique in Cisco routers called IPsef or Cisco Express Forwarding. And the default behavior of Cisco Express Forwarding is to do per destination load balancing, not per packet load balancing, which means that I do some Boolean math and I calculate destination pairs like source address, source MAC, destination MAC, and then based on those characteristics, that traffic will always take the same path. So you have to understand, in order to manipulate and understand how load balancing works, you also have to have a good understanding of how Ceph works. We're not going to get into the Ceph discussion right now, but I'm going to show you a couple of things about that as we go through the discovery here. So we're going to take a look at a discovery that allows us to essentially identify how load balancing works in EIGRP. Right now we've got a 4 meg link here, we got a 4 meg link here, and we've got a 1 meg link. So what we're seeing in the distribution algorithm is that these 2 links are being equally load balanced because by default that's how EIGRP load balances. But what we'd like to do is we'd like to trick EIGRP. Not really trick, we just want to convince EIGRP to use all 3 paths. It's the only protocol that actually has that capability to do unequal cost load balancing. There is no other routing protocol that has this capability. So let me go into HQ real quick. I'll do a quick ping to my destination, my test destination, which is my loopback, 192.168.0.1. Of course, the ping goes through. All right, and if I look at my routing table, show IP route, EIGRP, and sure enough, I can see 409.600, 409.600, and so on. So we're doing equal cost load balancing. If I do my show IP EIGRP topology, I can actually see all 3 routes are available, which means I have a feasible successor, by the way. That's an actually really important concept. I'm going to talk about that in a minute. We already know what a feasible successor is, but when it comes to load balancing, there's a very important concept to feasible successors in load balancing as well. So we know that this route's not going to be used because it simply has a higher metric than the other 2 routes, and we have two successors and 1 feasible successor because the reported distance is less than the feasible distance of the primary path. All right. So what I'd like to do is I'd like to be able to trick EIGRP into using all 3 paths. And the way that we do that is we manipulate a value called variance. So let me get down to where we were. There's my ping. There's our route, there's our topology. We're going to use something called variance. Variance is simply a multiplier against the best metric. Let's say, for example, I have 2 paths that have a cost of 10, and I have a 3rd path that has the cost of 20. If I want to use all 3 paths, I put in a variance of 2, because 2 times 10 is 20, which means that anything from 10 to 20 would be considered equal. Does that make sense? That's as simple as it gets. It's just simply a multiplier against the metric for the best path. The default variance value is 1, which means that we're multiplying the best metric times 1, which means that only paths that have that exact metric would be considered equal. Maximum is 128. I don't know that you would ever set your variance to that high because that pretty much would include just about every route probably. But the reality is that we want to go ahead and make sure that all of our paths are used. All right. So if you do the math, this metric is 2297856. This metric is 409600. If I take my 22 value, let me get back to my calculator here. If I take my 2297856 and I divide it by 409600, I get 5.61. So I need at least a multiple of 6 to include that alternate path. Quite simple. All right. I simply need a multiple of 6. You can see the calculation down here. So let's go ahead and implement that on our HQ router. All right. Config T. Let me do a show IP protocol. Oh, it's one. It's on the diagram here. Router EIGRP 1, variance 6. That's it. Do a show IP route, EIGRP, show IP route, EIGRP, and you can now see that we are including all 3 paths in the routing table. Because this number times 6 is greater than that number, which means it's included within the range. Now, what I was mentioning before is this idea of a feasible successor or the feasibility condition. The routes that are included in the variance are only routes that qualify as successors and feasible successors. Any route that falls within the variance threshold that does not qualify as a feasible successor would not be used even if it falls within the range that you specified. All right? Very important concept to understand. Another important concept to understand is to understand the impact of only doing this on one side. We have asymmetric routing now. HQ thinks that it can load balance over these 3 networks. And if I do a show IP route 192.168.0.0, I can even see that the traffic share count is much higher for these links than it is for this link. By the way, traffic share count, there's a formula that goes into calculating that. It doesn't directly correspond to packets. Like I'm not going to send 240 packets over the other 2 links for every 43 packets I send over the slower link. That's not really what it means. There's actually some algorithm that's used to calculate the traffic share count value. We don't really need to get into the details of that. But essentially, that's what we're doing. We're doing unequal cost load balancing. More traffic is going over 2.2 and 1.2 than over 3.2. Maybe. Remember, IPsec might throw a wrench into that because it does the per destination load balancing by default as opposed to per packet. So one of the things that you'd want to do is you'd want to optimize IPsec by changing the load sharing algorithm to some sort of other method. We don't have to get into the specifics, but I can't even remember the syntax that I use.
Is that like the MAC, destination MAC, source MAC?
Well, that's what we do in like Ether channel, but it is, yeah, it's basically the same concept. Yeah, same concept. There was a command to change the load sharing method, but we don't need to, I'd have to kind of go through and maybe discover what's included in the hashing function and all that, but we don't have to get into that. Just something that you definitely need to consider. If you want to do true load sharing, we would just disable Ceph, but then you're going to do process switching or process routing, which is even worse. All the packets have to go up to the control plane for processing. So just keep in mind, if you're going to do this unequal cost load balancing, you need to make sure that you understand the impact of Ceph on that environment as well. But here's the other thing. We didn't do anything on the return path. We're doing this load balancing, so all three paths are being used to go over to BR, but I didn't do the same thing on BR. So if I come into BR and I do a show IP route, for the routes that are coming back from HQ, well, I guess I need to add one. Do show IP interface brief. Let me just add one real quick. Interface loopback 0, IP address 1.1.1.1. Router EIGR, don't know why I just did that. Network 1.0.0.0. Okay. So now if I go back to my BR router, I'll see the 1.0 subnet, but you'll notice I haven't applied a variance to this side. So it's going to, if I did a source ping from the loopback, it would use all three interfaces or whatever traffic I'm generating from that router, whatever it is. It would use all three interfaces to go in one direction, but it would only use two interfaces to go back. So you need to make sure that if you want symmetric routing, that you'd also have to go into the EIGRP process here and put in the same variance so that you would see, oh my gosh, you would see that all three routes are being used in this particular case as well. Come on, break. There we go. Show IP route, EIGRP, and now we're doing symmetric routing, and the traffic share count is going to be the same as well, right? Show IP route 1.1.1.0, and sure enough, we see 240 and 43. So we're actually really doing true asymmetric routing in this case. All right. I mean, that's pretty much it for variance. There's not much else to it. You can see the variance option when you do a show IP protocols. Show IP protocols, and you can see that the variance is applied. But let me mention one more thing. The book doesn't mention this, but what if I just wanted to disable load balancing altogether? I don't want to do any load balancing. I just want to use one path. Go into your router configuration and do maximum paths 1. And do the same thing on the HQ side because we want it to be symmetric. Maximum paths 1. Doesn't mean that the other paths can't be used. If I do a show IP EIGRP topology, I still see all three paths. And in fact, both of these paths have the same metric, but now I only have one successor. All right. Show IP route. And we're using the path through 1.2. All right. Happens to be the lower address. I mean, that's really the only deciding factor in this case is which one comes first. And that's how it turns out. All right.
Now, with that, if you did that on the other side, would that take the same path, traffic, because that's the same.
Yes. Yes, it would take the same path. You would, of course, want to verify that, right? But so do show IP route EIGRP, so it's the one subnet. And there's a mathematical calculation that it uses to determine which path to use. I would say that it's just the first one that shows up in the list, but that's usually never the case. But it would typically be symmetric because of the way the routing table is actually built. They're built the same way in both processes. Okay. Well, that didn't take too long, so we're done with that lesson. Lesson number 3. Tomorrow we're going to finish up EIGRP in the morning by talking about EIGRP for IPv6. And then we're going to get into some named configurations where we're going to talk about how to set up named configurations. The great thing about EIGRP for IPv6, the only thing you need to know is syntax, because everything else we talked about, successor, feasibility condition, variance, maximum paths, everything is exactly the same in IPv6. The theory does not change at all. So it's really just a matter of learning syntax. So that's what we're going to do, and then we'll go ahead and take a look at named configurations after that as well. All right, so thanks for sticking it out a little bit later today. I didn't want to get too far behind. I think we're maybe about 3 hours behind by now, but you know, again, it's always about quality, not quantity, so I want to make sure that you guys are getting the most out of these lessons. All right, so we'll see you guys in the morning.